Okay, so we're gonna quickly move along here, and we will now be listening to Shihao about Solidity basics. Please,
Yes.
take it away.
Was that intentional? Okay. I'm gonna put my presentation here. Okay, wow, we are a lot of guys here actually. So my name is Shihao Poon. I was on the other workshop we had 1 week ago. So last time we spoke about Remix, Web3.js and Truffle. So now we are going to speak about Solidity, actually how to code in Ethereum. So most of you may wonder why I have this band-aid, but just a small story is that I'm taking care of my sister's rabbit, and then the rabbit jumped on me, like the Monty Python video, you know. So that's why I have this band-aid. Okay. So today my goal is to show you an overview of Solidity. It will go quite fast, so I think after this presentation you will not be able to code. You will be able to code Ethereum, but you will not be an expert, so to say. So we have a Slack channel, as you already know. So if you are not on the Slack channel, please join it. Johan, could you post the link on meetup.com? So those guys who are not on the Slack channel can join.
I don't have the link, else I could do it.
Okay, we will put the link, invite link somewhere later. Okay, so let's start. So let's begin what a smart contract is. A smart contract, I used to think of it as a web service. We have a lot of web services on the internet. You can see a web service as a unit in a system. We have a lot of web services that provide us with information and data and stuff like that. And a web service has a API. You access an API, and yeah. And a web service also has an identifier. You have an IP address. You reach the web service using a IP address. But for a smart contract, you reach it using the contract address, a hex code that is 20 bytes, 40 characters. If you add 0x, is 42 characters. And then you can do calls. You can do HTTP requests using the HTTP protocol to a web service. But if you look on the smart contracts, you do transactions to the smart contracts, calls. So, and in Ethereum, there are 2 different account types. You have the external account, we call it the Ethereum wallet. A Ethereum wallet has an address, this 20 bytes characters, and you have Ethereum wallet can have a balance, and it has an address. You can send Ether from one address to another address, receive Ether. And then you have the contracts. So I think the contract is the most important stuff. In this contract contains Solidity code. That's why we are here, actually. And a contract can have an address. It can have a balance, and you can send Ether and receive Ether with a contract. So As you see, it's very basic right now, but I will show more and more advanced stuff as we go. So how is an Ethereum address created? It's many steps, actually. You can read the yellow paper how to create an Ethereum address, but I used to think it in 4 steps to understand it a little bit. So the first step is you create a random key that is 32 bytes, 64 characters, and then you derive the public key from the private key using ECDSA. It's an algorithm. And then you will have 64 bytes. Your public key will be 64 bytes. And then you use the famous KShack256 hash algorithm to produce a hash that is 32 bytes. And the standard hashing algorithm today is called SHA-3, but it was invented after the KShack256. But it's similar, KShack256 and SHA-3. And the last step, you just drop the 12 first bytes, and then you will have 20 bytes left, and that's the Ethereum address. So these are the global units you can use on Ethereum. There are more, but the most common ones. Wei, the smallest unit, and 1 ether is 10 to the power of 18 Wei. And then you have Finny, Zaspo, and you have some time units, second, minutes, hours, days, weeks, and years. And then we have some special variables and functions. If you want to know something about the block, you can use the block variable. If you want to know the gas limit, just write block.gas limit or the timestamp. Yeah. And then if you want to know something about the transaction message, you want to know maybe who the sender is, you can call message.sender. This is the most common one, I think, to know who the sender is. And you just want to know how much ether he did the transaction with, you can write message.value. So those two are the most common ones in a Solidity contract. And then you have data types. In most of programming language, you have a lot of data types, but these are like the ones you will use. Maybe some more, but this is the most common ones. I think you can do almost everything with those data types. And then we have the hash table. This one, you write mapping, and then you write a key and a value. Here we says that the key is 32 bytes and the value is an address. An address is, as I said before, 20 bytes. So in this contract, you have a contract called user. You can register users by someone writes a string, and then it checks that it's empty, the entity in the hash table users. And then if it's empty, it will put the address inside the hash table. And the unregistered will just empty the entity in the hash table.
What about concurrency there?
Sorry?
Concurrency in the function? How is that being handled?
Concurrency.
If multiple requests are being made to the contract.
Multiple. Aha, you mean?
Threads, but there are no threads.
Yeah, there are no threads. And then you code in.
Yeah, but it can be like different processes. It doesn't have to be threads.
I don't think so.
Machine actually. It won't happen.
Yeah, it won't happen.
It's just one thing at a time.
Mm-hmm.
The whole EVM
Exactly.
is a stack machine, so it's basically stepping one instruction at a time, and the closest thing to that is reentrancy, which is not the same as multiple
Exactly.
threads.
There will be never simultaneously. It will always be one after another sequentially, I think.
Mm-hmm.
Yes. And in normal programming we have structs and enums, and in a Solidity contract we have the same struct called voter with 4 different variables, and we have enum. We just write it like this. Enum called state with 3 different types. Normal programming. And in Solidity, you have 4 different visibility for a function. You have the external one, meaning that only external contracts can call this function. And you have public, everyone can call this function, any contract. And then you have internal, only contracts, functions that is internally, only the current contract can call this function, or contracts that derive from the current contract can call those functions. So we have private, only the current contract can call this function. So I mean, we have this in normal programming also, so it's nothing new. And inheritance, normal programming, we have inheritance. In Java, we just write colon to do the inheritance, but and in C# we write in C# you write colon, and in Java you write extends. But in Solidity you write is. Mortal is owned, so that means Mortal have access to this function here and the variable here, because this one is the owned contract, and base 1 here it's from Mortal.
And the basic, the default visibility, what is that?
Sorry, the
Default visibility, what is that?
if you don't write anything, I think it will be public.
Public, yes.
Yes, public. So if you want to change the visibility, you have to write it. Okay, everyone knows what I'm talking about. Cool. And we have the abstract and interface in Solidity. So here we have a contract called filling. Is a function, but this function doesn't have an implementation. That means that this contract is an abstract contract, and the ones that derive from this abstract contract needs to have the implementation of that function utterance. Here is the implementation. So if you want to write an interface, you just write interface. And here we have the function without implementation.
What is the difference between those two, like abstract and the interface?
Sorry?
What is the difference between interface and abstract?
The difference is the abstract can have functions with implementations. You can write another function with an implementation, but in an interface you can only have functions without implementation. So it's the same, I think, in almost all the programming languages. So nothing special at all. So they have the same behavior as C# and Java in this case. So, and this thing is kind of special when it comes to Solidity code. You can write functions with a constant keyword here. That means that this function is only read-only. It doesn't change the state in the blockchain. So that also means that it's free to call this function. It's completely free. You don't have to pay any gas, don't have to put any values in a transaction. So it's free to call this one, because this one only calls the local node that's in your local machine. You don't have to, if you want to change a state, you have to sync with all the nodes. Because if you, for example, this store data, I set the value on the store data, that means that I changed the state, and then all the nodes have to sync this state.
Is it enforced? So if I try to set the variable in a constant function, does it throw, or what happens? Doesn't it compile?
I think it will not compile actually. I think Remix will say, hey, why are you trying to change the state? So you can only, it's only read only this function. Very important to know about if you want to code optimized
So every getter method could be constant?
Yeah, could be, but always write constant if you don't want to, if you want the function to be free.
Can they take arguments also?
This one can take arguments. It can take thousands of arguments.
So how can it not consume gas?
Because you don't change the state.
Yeah, but every instruction in the machine that you execute will cost gas. So I don't. If it was completely constant, it could be done at compile time, and then it could be free. Then it could just be a memory pointer, but not really completely free because memory was cost.
Even if you run a really expensive neural network or something, then
No, so I'm not saying it's expensive. It can probably be cheap, but I can't see that it's free.
Yeah.
Or is
Maybe
it?
we can try that. I don't know. I haven't tested it that much, but we can try it actually.
Yeah, so I'm thinking if it were completely free, you should be able to DDoS also using this, right? So there has to be a way to stop the stack machine from getting stuck.
Yeah, that's what I read about. Maybe if you add parameters here. I don't know actually, but let's test that. And then we have the payable keyword. That means that you can send the ether with the transaction to the contract, to this simple auction contract. So you know when you do a transaction, you can say how much gas you want, the gas limit. You can write the gas price, and then you can have a payload, and then you can have a value, meaning how much ether you want to send. And this payable means that you can send ether to this function. And this is address-related functions. You can call this balance to check the balance. You can transfer ether with this transfer function. You can send. The difference is that send returns false, and you can do stuff after, whereas transfer throws on failure, and you can't do stuff after. And then you have some low-level calls. You have this call, you have call code, and delegate call. It's low-level calls, and you shouldn't use them if you are not sure what you are doing. So there is two different types of transactions. There is transaction and message calls. Message calls is transaction between contracts, and you can't do a message call without doing a transaction, because Ethereum wallet has to do a transaction before a contract can do a call to another contract. So that's a message call, and then you have transaction. There's two different transaction calls. Send transactions that change the state of the blockchain, and that will cost ether and gas. And then you have calls, and call is when you use the constant keyword, as I showed you before, and that doesn't change the state of the blockchain. It's read-only, and it's fast, and yeah, it's executed locally on the user's local machine. And then you have those three low-level calls I mentioned before. Call, delegate call, and call code. And those three calls breaks the type safety in Solidity. So you should never use them if you're not sure what you're doing, because many hacks has been produced because of contracts that use these three different calls. For example, the DAO hack, if you have heard about it, someone saw that this low-level call was used, and then some attacker exploited this smart contract. So what's the difference between those three calls? With these low-level calls, you can call functions, you can send ether with these three calls. Here's an example. When A does a call on B, the code will run in the context of B. So if you call this on the B contract, that means that this is B. The keyword this will be B. If you A does a call code on B, the code runs in the context of A. That means if you call this, it will be the contract A.
Do you have access to all the variables, etc. via this?
Yes. And delegate call. A invokes B, B does delegate call on C. The code C run is in the context of A. So if you have three different contracts that call each other like this, then if you call this in the contract C, you will have the contract A. It will reference to the contract A. So I'm gonna show you a example here with Solidity code, how it is used. So this is pretty advanced, so not basic stuff anymore. So you have contract A, B, and C, and we have three functions in the B contract. This function here does a call, a low-level call. This function here does a low-level call code, and this one does a delegate call. So all these three functions will call the C contract. We'll call the set end. Set end is here. It's this function here. And this one just sets the sender variable. Sender equals message.sender. So message.sender is the sender, actually. If someone calls this function here called set n. This function will call set n. Message.sender will be the contract C. Is it too light, or should we? Does everybody see what the code here? Okay, perfect. So if this function is called call code, this will call set n, but message.sender will not reference this contract, it will reference the B contract. So there's a difference on these two. If you do a delegate call here, it will call this set n, and it will reference the B contract. So these two will do the same. But we have another contract, contract A. If we do a delegate call set n, which will call this function here, and this function will call set n, then the message sender will reference contract A. But if you call this function bar will do a call code set n, this function here, and this function calls set n. So that means that message.sender will reference contract B and not contract A. So it's pretty confusing, but that's the difference in those three calls. Maybe you don't understand it, but come to the Slack channel and we can talk.
Yeah, question.
Yes?
The delegate call, how transitive is it? Does it always find the first caller in the chain?
Yes.
Always.
It's,
so if you have 4 steps, it would actually go back
Yep.
to the very originator of the
Yes.
whole.
Yes, because it's delegating.
Right. And call code only goes back one.
Yeah.
Okay, so there's no way to find if you have for the third and the second step.
Exactly.
Okay, yeah.
That's how I understand it. Normally, I try to not use these low-level functions because then someone could find a hack like the DAO hack. Okay, one picture is missing. Let's see what happened to my picture. Maybe I can speak without that picture. No, I need it. Let's speak without this picture. Okay, so I had a contract here. It was a normal contract, and it had an import convert lib on the row. And that means if you do an import, that means you reference this code with this code. And a library is also some kind of contract. But every time someone writes like this in the convert lib, that will reference to the one that is important, that has imported this convert lib. So it's yeah. If you want to, you can see this as a base class in normal programming.
But is it kind of like it gets inline in practice?
I don't know in practice how it looks like in the bytecode, but maybe you can see it as inline, I don't know. The only thing... Yeah?
Did you check with when we deployed with Truffle if it got an own contract address?
Yes, it has an own contract address actually.
Yeah, then it shouldn't be included in the bytecode.
Yeah, so if you want to connect a library with a contract, as I showed you from the previous workshop, you have to link them. If you don't link them, they will not know each other. so you have to use link. Yep. And then in Solidity you can create your own modifiers. And a modifier is you can have a piece of code where you check a special condition. So if you call this set contact information, it uses the only owner modifier. That means before this code executes, it has to
How would you like to make $1,500?
Say yes.
yeah.
You send that to me, please.
Yeah, to me too. Okay, so yes, before this code executes, it will check this condition, this if condition. If the sender is not the owner, then it will throw. And this underscore is this code here. If you put this underscore above the if sentence, then it will run this code and then after this code. So this is just to
Placeholder.
yeah, if you're lazy, you just write an underscore. So yeah, it's very easy to create your own modifiers. And then we have WebSocket provider. In Ethereum, you have something called events. Maybe someone executes a function in your contract, and you want to have something that says that the function has been executed. Then you need events, and from outside a smart contract, maybe you have a piece of JavaScript code. You can subscribe to those events, a subscription, and then you will be able to know what's happening inside the smart contract when someone calls a function. So you need the WebSocket provider. If you have a web application, you need the WebSocket provider to be able to do subscriptions. Normally, when you use Web3.js, you have the HTTP provider, but this HTTP provider doesn't support subscription anymore. And then you have to use the WebSocket provider. And there's another strange thing, that Ethereum.js test RPC, you use that to spin up a node. I showed you on the previous workshop that you could spin up a node with 7 characters. You just write test RPC on a terminal, and then you have a node. And so WebSocket provider is not supported on Ethereum.js test RPC, so it's a bit hassle to make everything to use this subscription thing to subscribe on events. So this is how you spin up connect to the test no, connect to the mainnet. You can write use get and write these lines, and then you have to write these parameters: VS port. You can choose whatever port you like, and VS origins all. Then you will be able to subscribe on smart contracts in the mainnet. I think it's a new thing, but because when I could before use the HTTP provider, so stuff is changing all the time.
Do you have events in smart contracts?
Yes, I'm gonna show you now.
All right.
If you here's a smart contract. No, here's a smart contract. If you want to create your event, you just write event get complete. You will is complete. This will if you use this get complete event, you can return a new int unsigned integer. In this case, you will return 666 if this get is accessed. So this code here is some JavaScript code. I think I showed you on the previous workshop how to deploy a contract. You use requires on Web3, so you can use Web3.js. You can require FS to read plain text files, and then you have Solk to compile your Solidity code. Here we can see how I use the WebSocket provider. I want to connect to localhost 8546, and then I have already used get to connect to the mainnet, maybe. So once you have Web3, you can do a lot of stuff. Here I read hello event. This is hello event. I read it in plain text. So source will be this code here, plain text. Then you can compile the code there, and then you will get a JSON here, compile contract in JSON. And then you can get the interface and the bytecode. And you need those to deploy the contract. Here I create a new contract using the interface, ABI, application binary interface. And then here I deploy using the bytecode. I say that it's from this Ethereum address. I use 210,000 gas. Gas price is 1. And as you already know from the previous workshop, it uses promises everywhere, most of the functions. So if this is successfully deploys the contract, then you will come to this function here. We get a contract instance. And when you have a contract instance, you can subscribe to the event. Here we write contract instance events get complete. Get complete is this event here. So now I'm subscribing to that event. So if the get complete event is called, then I will go inside this function here, and it will just console log 666 if someone calls the get method. So to try that, I just do it here. I call the get method with a Ethereum wallet, and yeah, and then it will write console log 666. So events is really powerful, and you need it to know what's happening inside the contract.
Would that be a primary way to connect other services to the contracts?
How do you mean with other services? For example?
Let's say you have some web-based service that does something surrounding your contract.
Yeah.
Would that be a way that you can reach up on?
Yeah, you can connect them and communicate between a web application and the contract with events.
And that would be the typical way to do it?
Yes.
One thing, sorry.
Yes.
So what do you need in the last line, the second function, why is that needed?
This one.
Since we already registered the event listener with console.
Yeah, this function here,
because
get returns
the 4, that's for the
So
okay.
it will write console log 4 here.
Right.
So yeah. Maybe you don't want to know about the 4, then you can remove the function here.
Yeah, but you can only return like this event with like everything inside, and you don't need that.
Yeah, but the main thing with this function is what it returns here. that's more important than this event here, I think.
Yeah, but event can also contain a value which is going to be
Yeah,
returned.
but without this return for, this function doesn't have any return value. It says returns due integer. So I think this one is more important than this.
Okay, but I mean, the real use of it is by you can send a notification
Yes.
in line before it returns, and maybe more
Exactly. Return is always in the, not always on the bottom, but most of the time it's on the bottom. But event, you can put it anywhere
But
in
the
the
problem
code.
can be because these two things are not atomic, so you can send an event, but the return will not happen eventually, and then because if you do
This
just one
will,
thing, like, then it's atomic.
both of them will happen.
Well, if you have
If you
throw
have
after
throw
get
in
complete, then probably it will not happen.
Sorry?
If you have throw after the get complete, then
Ah,
the
yeah.
return will not happen.
Yeah.
I hope the event doesn't trigger it.
Uh-huh.
Hopefully.
Yeah, maybe it will not trigger then. Yeah, that's, yeah.
Yeah.
Well, yeah, if you throw it, the transaction is going to fail and the event will not be logged in the block.
Exactly.
Yeah.
The event is actually logged somewhere in the block. That is how we read it from Web3.js.
But maybe if you work with events, you maybe don't have use return values. You just fire and forget and wait for the event to get back.
Yeah.
Maybe. I don't
Yeah,
know.
maybe.
Does it write to the log or the store?
Sorry?
Does it write to the log or the store?
No, it's a special thing in
The machine only has log or store.
it's not storage in the contract. It's a special storage that is for logging.
The log.
Yeah. So it's a special thing which is for logging. So the contract will issue the log event, and then it will just continue. And when the transaction has completed, we can read that from the blockchain thanks to the thing on the right.
Yeah, but the event is not visible to anybody until that box gets micro somebody.
Yeah, the transaction has to finish and the block has to finish.
Right.
Then the event will be visible. So we can't wait for the event in the same function. The off-chain service can then transact back to the contract using a callback function. That will be a whole new block then,
Right.
Yeah.
the next block, perhaps.
I mean, it's easy to think that with a real-time event, but it's not. It's just following the blocks. and
Yes.
everything else.
Yeah, so this looks like JavaScript and it has events, but it's not the same, really the same thing.
Yeah. Okay, I continue. Then I mentioned that someone asked how to self-destruct a contract from the previous workshop, and this is how you do it. When this contract is created, message.sender, the one who created the contract, will be the owner. And if someone calls this kill, you will check that the sender is actually the owner. If it's not the owner, then you will not be able to self-destruct. But if it is the owner, then this will be called self-destruct, and you write the address here where all the funds in a contract will be sent to. If I have 100 million ether in this killer contract, then it will be sent to this owner.
Big answer.
Yep. So maybe you should try and kill contracts. Maybe you're lucky and receive some ether. Maybe kill an ICO.
I actually saw on a contract on an ICO,
Okay.
someone tried to call the withdraw function
Ah.
with a bad instruction as reasons, but he tried
Okay.
to.
I'm gonna show you how to do a hack later. How to do the DAO hack. Because that's similar. And in Solidity you have.
One quick question about the self-destruct. what's next? I mean, once you record that, then what happens?
I think I don't know exactly what happens actually. Thomas, do you know what exactly happens?
It's supposed to just disappear from the blockchain.
Mm.
Yeah, the code will always be
So
there.
it's just marked as a contract which will never be, which cannot be executed anymore.
Or I think you can't interact with the contract. It's not there, I think. I haven't actually tried it. But it's supposed to be.
The code will always be there.
Yeah,
but
but
the
why
contract
will it always be there if it's self-destructed?
You can't remove stuff from the blockchain.
Yeah, it's on the chain. I mean, you don't delete from the chain.
You can't find
You
it
just
in the
cannot
next
execute
block.
it anymore.
Yeah.
So it will be in the history, but you can't refer to it in the next block.
Exactly.
I would bet my Satoshis on that.
Yes. Okay, I'll continue. We have 4 different error handling things. We have assert, require, revert, and then we have throw. So a assert is to try to test for internal errors. It's usually in the end. You check that everything worked in the end. That's how you use assert, like in normal programming. And then you have required to check, maybe you check inputs in a function. You check that the input parameters are correct. Maybe you don't want people to be able to send less than 1 ether, then you can have a condition in the beginning. Or you can have a modifier. Reverts the transaction. And in Metropolis, when after the Metropolis release, I don't know if Metropolis is 2 parts. It's Byzantium and then it's Constantinople. And they said that after the Metropolis release, that if revert is called, then the gas left will be sent back to the sender. Whereas if you do a throw, all gas will be gone. So yeah, easy to remember those 4 types.
What does revert the call mean? I mean, what's different from require?
You said revert and
Require. What's the difference? What does
revert. Revert is like a throw. If you write revert, then yeah, the contract ends. And you said require, right? Requires checks a condition and then it can continue after that if the condition is true.
Okay. Yeah.
Yes. Now to some more advanced stuff called oracles. Sometimes you want to get data from a web service or from the real world somehow. Then you can use something called oracles. So here we have the oracle contract, and here we have someone that wants to use the oracle. This oracle users trusts this contract, and the oracle user wants to be completely sure that transaction from the oracle user to the oracle is safe, and that responses from the oracle is from the oracle contract. So then you can do this code here. Here we just create an instance to the oracle contract, and we specify the address to this oracle contract here. And then we have a function here called buy something. Someone wants to check the USD rate. So he will make a query to ask for the USD rate. And then this oracle will respond with something, with a ratio. And then you have the oracle response here. The response from this contract will actually be here. So this oracle here, it has an struct that contains byte data, and it contains a function. It's external, meaning that this function doesn't exist in here. It should exist somewhere else. Then you have an array that where you can push a struct to this variable. And then you have a function here that will push requests to this array here with some data and a function. And then we have a reply function which will fetch from the hash from the array and call functions. So it's pretty advanced. Everything starts with that someone calls this function buy something. They want to check the USD ratio, and a query will be made. USD string will be sent with a function. Oracle response is this function. So this whole function will be sent to the oracle. So then we will end up in this function query from here to here. And this query will just push the byte and the function in an array. So you can call this multiple times, and it will just add more requests to this array. So then,
where is the response stored in this example? Because Oracle response should, I guess, return response or store it somewhere.
Oracle response is here. This top of Oracle response.
Yeah, but where the actual response, like what it is to return, I guess needs to be stored somewhere.
You mean the response?
Yeah, that's the use the data comment, right?
If you query for something like USD, so you get some response back, like some value number, whatever.
Yeah. I'm coming to the response. What's happened? How you get the response? So someone will call this reply method. Maybe the one who owns this contract. Someone in the real world who owns this contract will call the reply. He wants to reply the USD ratio. So because this contract is trusted, so everything that comes from this contract, the Oracle user will trust that. So what happens if when someone in the real world calls this reply, it will do a fetch the request, and then it will make the call. And when this function is called, it will actually call this function here.
Yeah. So where is the response returned? How it should get the actual response?
And the guy who called this reply also made a transaction with the response. So the response will end up here.
Like the ratio, the actual ratio, whatever.
Yeah, the ratio. The real world guy will come with the ratio, and here the ratio, and the ratio will end up here. and then you can you have the ratio in this function. But first, before you can use this ratio, is require here, as you see, and the require checks that it's actually the message sender, the one who sent to use this Oracle response is the Oracle.
So in a more real-world example, maybe you would send a message in the query method to somebody so they can find out that somebody wants a reply.
An event?
Yeah, an event.
Yeah, I guess
Someone-
you need to send out the actual response somehow to the guy who is calling this web service.
Yeah, I mean, if you were to add an event in the query method just to notify some JavaScript thing that somebody has sent me a query.
Yeah, so you can add an event here actually. Yeah, that's correct. Maybe the real guy person doesn't know that someone has made a query with this code. So you need an event.
Yeah, or a timer or something.
Yeah, and someone subscribes to that event, and when he knows that someone has called this query, you can the real world guy will call the reply function to reply with the USD ratio.
Do you know why the request ID is in this example?
Request ID, you mean this?
Yeah.
Because every request is unique.
Yeah. But if I would like to broadcast something to all requests,
maybe someone writes SEK, wants the SEK ratio,
okay.
or maybe someone wants some other ratio, then this request will grow.
So the array, the request array is more like a hash.
Yes,
hash
it's
table.
yeah, you can see it as a hash table. In this example, they used an array.
Yeah.
So yes.
Two questions. The
Yeah.
first is that number when you create Oracle, what is
This
that?
number, this is an address.
For the
This is a false address. It should be 20 characters, but lazy.
How do you know that number?
Sorry?
How do you get that number?
You can use. You can actually write a constructor to set to this address, but this person who wrote this already know that it will always be this contract that is trusted. But you can do a constructor, or you can make a function that changes who you trust.
One more question.
Yes?
The guy that is using this, will he use both Oracle user and Oracle, or?
I think in the normal world, so Oracle user is someone and Oracle is someone else. They are not connected somehow. They are not partners or anything. They just this guy here trusts this contract. So, for example, this could be Forex. They have all the ratios, and you trust Forex. Then you write their address here, and you trust them.
Who is paying the execution fee? Is that the Oracle user or your Oracle?
This guy will probably pay
The change of the requests array, because that's the state change.
Let me see.
When you make a query, you add a
Yeah,
request
this
to the
guy
request.
pays for the gas. This guy calls query, and you will end up here, and the thing that happens here, it's
But it's not the message sender who is actually paying, the one who invokes the
the
query
message
method by
sender.
something?
The message sender is
Yeah.
the payer.
Yeah.
So the guy who executed by something also pays for the query function.
Yeah.
and the guy who responds have to pay for the reply.
Why? Why would you pay?
In a normal situation, it will be not like this. This is just an example. In a normal situation, maybe this will not execute. You can write a require here that says you must pay me 100,000 ether, and if it's not 100,000 ether, then you can throw, so that the transaction fails. So if this guy pays 200,000 ether, then everything will execute. So you can have a condition here.
Can you do in the function call transfer a value to the function you're?
Yes, you can transfer ether from here to here.
Is there a syntax for that in the call?
Here you don't have, this is just a function call, but if you want to send ether, you can write message.sender. You write the address and the send or transfer method. I can show you what you can do. Here, these you can use to transfer ether. These are low-level calls, and this is normal calls. Those two are recommended. So how much time do I have left, Thomas?
Minus 10 minutes.
Minus. Oops. Okay. So I have a last slide. The most interesting stuff is, I think, the DAO hack. Maybe for 1.5 years ago, one of the first ICO gathered like more than 1 billion SEK.
$150
million. So that is more like 1 billion SEK. And that smart contract hold all the funds, and it got hacked. So 1/3 was drained to another contract. So very scary, and I was in that ICO. So when I was at work and I looked on Slack, and everybody was panicking. This guy called Griff, he couldn't handle the situation. He was one of the guys who created that. So we were writing, oh, it's bad. And then I was on work, I couldn't work because I knew that I had invested and money was
and we had to release it a day after. No?
Yeah, I was so stressed. I couldn't work that day.
It was funny because there was someone in the Slack channel who was shouting, "Shut it down! Shut it down!"
Exactly. And there were so many trolls who wrote stuff all the time. it was 10,000 people in the Slack channel. So today I'm gonna describe how the DAO attack actually happened. This is just simple versions. So we have a contract called victim. They have a hash table that says what the balance is for each user. Users just can put money in this contract in this anonymous function. When you sell ether, it will say how much ether you have in this hash table. Just it's 0 from the beginning, and you add the balance.
Is the anonymous function always like this happens when somebody sends me ether, or how's that thing?
No, normally you have another. This is just to make it more simple, but normally you have like a function send. You call it send.
Okay.
This is anonymous. If you make a call if you don't write which function you're calling, you will go to the anonymous function. So if you do the withdraw function, you have a if condition here that does a low-level call. And the guy who wrote this line who thought that message sender was always a Ethereum wallet. Always. So this will just send Ether to the sender who calls this withdraw. And then the balance will be 0. And then we have the attacker contract, the interesting stuff here. We have an instance variable called b that reference to that contract. And then we have a constructor that sets a reference to that contract. And then you have the attack method, which sends Ether, makes a call and sends Ether to the victim contract. And you will end up in this anonymous function because you haven't specified any method name. And then you have the withdraw function that will go to this withdraw function. And here you have a function that calls the withdraw function as long as the gas is over 100,000. So everything starts with someone calls attack, and then this row will send Ether the victim here, and you will have a store an entry in the hash table how much balance this user has, and then you will call the withdraw. Boom, we go here, and this will call a contract. Message sender is now a contract, not a Ethereum wallet. So this will call the anonymous function on the attacker, because he hasn't specified which function he's calling. So it goes to the anonymous function, which if the gas is higher than 100,000, it will call the withdraw function again before putting a 0. So it will be a loop. This will be called, and then this will be called, this will be called, and then back and forth until the gas is lower than 100,000. But this can happen in all eternity until the gas is lower than 100,000. So that's what happened actually in the DAO attack. And when the gas was lower than 100,000, then it set the balance to 0 in the hash table. So very scary. So avoid using this low-level call if not necessary. Yes.
So what could they have used instead of using
They could use, instead, if they only want to send Ether, they can use send or transfer.
And those existed?
Yeah, it was, you can use those two, because send, it has a default gas price. I think it is 21,000, so it can't do a loop. It's only 21,000 gas, so you can't loop it all the time.
But was there some reason they didn't use send? It's just a bad programmer.
It's a really skilled programmer actually who wrote the DAO contract, so I wouldn't say he's a bad programmer.
There's also another bug there. Yeah, that you're resetting the balance to 0, the last thing you're doing after you're sending, and it should be the other way around. So first you do the state change, and the last thing you do is to actually send the money.
So what if it fails?
Well, then the whole transaction fails.
Yeah. Of course, when the guy who called this attack function, he was like sending a lot of gas and had a high gas price. So this loop could loop. If you send like 21,000 gas, it will drain just a little bit, maybe some calls, a couple of calls.
And you have to stop while there is gas left, so the transaction can finalize.
Yeah.
That's why it has the check there.
So this is one of the most famous hacks, I think, because there was
$60
one.
million.
Yes, I think this should be one of the biggest hacks.
But the money is still sitting in the account, right? In the contract.
In the ETC.
I think no, there was a white hat group that did the same hack on the attacker contract.
On the attacker.
Yes, he had 1/3, so they created an attacker contract that attacked this one, because this did also a low-level call. I don't know exactly. This is not the true code. It's just a simple example to describe the attack.
So you should have self-destructed.
Yes. Well, and with you as owner, of course.
There was the contract you withdrew to was also part of the DAO somehow, so there was a 30-day limit in that contract that you couldn't withdraw it further from that contract in 30 days.
Exactly.
And that contract had the same vulnerability as the main DAO.
Yes.
So then you could draw from where you grew to, you could keep drawing. So the white hats started fighting, and it was. But I guess on the Ethereum Classic chain, they still have the funds.
Yeah, I got my funds back in the end because of the white hat group.
If they could just steal the money back?
Sorry?
Why did they hard fork if the white hat group?
They wasn't sure that they actually could steal the money back, because then the attacker could make another smart contract that drained the white hat contract and so on. Yeah, they had set some time limits for everything. It was like 7 days and 30 days, so they had to do the hard fork to really make it stop. Yes, I hope. Maybe I was a bit fast, but this is just to give you an overview of Solidity code, how to code Solidity code. I don't expect you to know exactly how to code Solidity after my presentation, but just an overview of what you can do and cannot do, and how contracts look like. Yes, I hope I managed to do that.
Excellent.
Yes, thank you.
Right, a small stretcher. Then the next.